section 3.4, rates of change. In this part of the section, we will talk about the velocity, speed, and acceleration. First of all, let's define the velocity. If we have s of t as a position function of an object that moves in a straight line, we know that the first derivative represents the velocity of the object. That means the first derivative, s prime of t, is the velocity of the object, and we can basically say the rate of change of the distance with respect to time. Of course, we're talking about the instantaneous rate of change. Now, if the velocity, the sign of the velocity indicates the direction of the motion. And for instance, if the position function is the height above the ground, then positive velocity indicates that the object is rising. The negative velocity indicates that the object is falling. Okay? Quite important information. Or sometimes we can say positive velocity indicates that the object is moving in the positive direction. Negative velocity indicates that the object is moving in the negative direction, if we will imagine like a straight line. Also, just to make sure that speed, yes, that we understand that speed is the absolute value of the velocity. Yeah? Doesn't really matter which way we're going, up and down, left or right. Speed is always positive. Absolute value of the velocity. And now, acceleration. The instantaneous rate of change of the velocity with respect to time, we will call the acceleration of the objects. Acceleration is the instantaneous rate of change of the velocity. This is the derivative of the velocity. Derivative of the velocity. Since velocity was the first derivative of the velocity is the second derivative of the position function, of the original function. It means the second derivative of the position function is the acceleration, or derivative, the rate of change of the velocity, how the velocity is changing. Is the velocity increasing or decreasing? Then we will know what is happening with the acceleration. And of course, we have also the Leibniz notation, the rate of change of the velocity with respect to time, or this is just the other notation indicating the second derivative of the position function with respect to time. We can see we did differentiate twice with respect to time, velocity and then acceleration. Okay, now let's talk a little bit about the velocity and speed. Yeah? We have four different situations, four different circumstances. All of the graphs represents them. And that's the situation of the object moving in the linear position, linear motion. And that's the position function, which the position function is changing with respect to time. All of these graphs represents different scenario with respect to the speeding up or slowing down. And we have to figure out in which situation, in which circumstances, the object is speeding up or slowing down. Let's take graph A. Okay, looking at the graph A, we definitely see that this graph has a slope. I can say slope is positive. I can even draw a couple of tangent lines, which they represents the slope of the curve, of course, slope of the tangent line. They are definitely positive. That means slope is positive. And also another thing that we may notice, the slopes, that the lines are getting steeper. Okay? That means the value of the slope is getting larger. Okay, now I can say that slope is positive. Slope is the rate of change, the instantaneous rate of change in this case. Velocity is positive. And velocity is getting larger then I can say velocity is increasing. Okay. Now, another notation, the same, all of the lines, all of the statements that I'm presenting, they actually describing exactly the same situation, actually the graph A. Okay, now I can use this, I can use a little bit of symbols. Velocity is positive, velocity is greater than 0. And since the velocity is increasing, its derivative is positive. As we remember, if we did have increasing function, then its derivative is positive. That's the concept that we were talking before. Okay, that means derivative of the velocity is also positive. This indicates the increasing. And we just learned that the derivative of the velocity is the acceleration. Okay, and if we have this situation, we can basically say, because everything is positive, speed is the absolute value of the velocity, but velocity is positive, then I can say that speed is increasing. Yes, speed is increasing since the slopes are getting steeper and the object in this case is speeding up. Okay. Of course, we're supposed to start this discussion because we're trying to figure out the situation speeding up or slowing down. Always the object is speeding up if the speed is increasing. Okay? If the speed is increasing, but sometimes we may get confused because of when we analyzing the velocity. Okay, that's when we're looking at the situation when the speed is increasing. Okay, but this is the condition. Okay, velocity positive, acceleration positive. Saying differently, we may say they have the same sign. Velocity positive, acceleration positive. That's the condition for speeding up. Okay, let's take graph B. Graph B has still positive slope. The slope is positive, positive, positive. However, the lines are getting less steep. Then they're getting smaller in values. In values, it will be smaller. This will be quite big, like slope, and then less, and it's almost approaching horizontal, but not. Okay, let's see the condition. Velocity is positive because slope is positive, and velocity is getting smaller. This means velocity is decreasing. Yes, we can see velocity is decreasing because the lines are getting less steeper. Velocity positive, velocity decreasing, its derivative, v prime, is less than 0. Because if a function is decreasing, its derivative is negative. And derivative of the velocity is the acceleration. I mean, this is the condition. Velocity positive, acceleration negative, and we may say that speed is decreasing since the slopes are getting less steeper. Then this is the case for the object to slow down. This is slowing down scenario. Graph C. Now we have actually negative. And we can see negative slope because the line is getting negative. Okay, we have definitely slope is negative and getting smaller negative because the lines are getting less, steeper. Okay, but we have to be extremely careful. Getting smaller in the negative direction. Yes, for instance, slope is -2, and then slope is -1, and then slope is -0.5, and then almost 0. Yes, they are getting closer to 0. No, -1/4. I mean, they are getting smaller negative, but when we will think about the number line and the actual values, the slopes the numbers are getting bigger, because -2 is a smaller number, for instance, when we compare to -1/4. Yeah? So we can say that the velocity is increasing in values. Getting smaller negative, we making numbers bigger. It means slope velocity is negative, that's okay. But this one, yeah, we have to be a little bit careful. It's getting smaller negative. This means that it's increasing in values. It's getting closer to 0. Velocity is increasing. And we have a little bit different situation. Velocity is negative and velocity is increasing. I mean, of course, if the velocity is increasing, its derivative is positive. Let's maybe look at this one. Velocity positive, derivative of the velocity, of course, is acceleration, it's positive. So in velocity positive, velocity negative, and acceleration positive. Yeah? This will be the situation that the speed is decreasing. Yeah? The speed is decreasing because speed is the absolute value of the velocity. When I take absolute value, then yes, the numbers are decreasing. Speed is decreasing, or graphically we can look at the steepness of the line. Not exactly the values, but steepness of the line will tell us that the slopes are getting less steeper. Then speed is decreasing, the object is slowing down. And we may notice both of them, velocity and acceleration, they have opposite signs. Then is slowing down. And we have one more, D. Let's draw a couple of slopes. One slope, another tangent, another tangent, another tangent. Definitely they are negative. Slope is negative. All of the slopes are negative. And they getting larger negative because the lines are getting steeper. Yeah? Larger negative. Again, we have to be extremely careful saying, describing decreasing or increasing, okay? Velocity, slope, negative, and getting larger negative means that we're decreasing the number. This slope, it could be -1/4. This slope could be -1/2. This one is steeper, -1. -2. So definitely the numbers itself are getting smaller. They decrease. Velocity, the slope of the tangent is the velocity. Slope of the line, slope of the tangent is decreasing. They are getting larger, but decreasing. But since they're getting larger, the speed is increasing. This is the situation for speeding up. Let's finish this. Velocity negative, velocity decreasing, derivative of the velocity is negative. Derivative of the velocity is acceleration. And we may notice in this box, both of them, velocity and acceleration, has the same sign. This is indication for speeding up. Okay? So always when you will see the graph of the position function, and if you can draw a tangent line, and if the tangent lines are getting steeper and steeper, this is the case for speeding up. If the tangent lines are getting less steeper, this will be the situation for slowing down. Okay? This represents, of course, the speed. I do have, this was the graphical explanation. I also have a little bit of, oh, that's actually the summary. That's the summary. Okay, let's look at this. Speeding up, we can see this was speeding up, A and D was speeding up. Velocity and acceleration positive, velocity and acceleration negative. The same sign. For slowing down, speed decreases. And with respect to the velocity acceleration, different sign. They are opposite in signs. That's how we can understand this situation. Okay, so we can look at the sine, we can look at the steepness of the tangent line. And this is a little bit of the same situation. You may pause the video or you may look at the slides later and try to, yes, understand, but this is the same concept, but just using the formulas. Excuse me. And that's what I want this to be like a summary. Object is speeding up if the velocity and acceleration, if they have the same sign. If they have opposite signs, object is slowing down. But we know the main idea is the speed. Yeah? Speed is increasing, or the slope of the tangent lines are getting steeper. Either way, positive or negative direction. Okay, and I have this example. You can also look at this example, read the question, read the description, and we will start with this exercise. Okay, let's see. A truck enters the off-ramp of a highway at t equals to 0. Its position on the off-ramp after t seconds is defined as s of t, 25t minus 0.3 t cube meters. On the interval, on the like from 0 to 5 seconds. 5 actually seconds. Okay, now we have two questions to answer. A, how fast is the truck going at the moment it enters the off-ramp? Okay, I mean how fast we have to figure out for part A, velocity at 0, because it enters the off-ramp when t is 0. Okay, first of all, we have to figure out the velocity. Velocity is, of course, the derivative. Let's compute the derivative of the position function. This is position function, third degree polynomial. 25t is 25 minus 0.3 t cubed, 0.3 times 3, 0.9 t squared. This is our formula for the velocity. And velocity at 0 at that moment, we can even say initial velocity, we will substitute instead of t 0. Of course, it's 0. V at 0 at the moment that it enters the off-ramp is 25 meters per second rate of change. Okay. And now the question B. Is the truck speeding up or slowing down on that time interval, like from 0 to 5 seconds? We have to figure out what is the velocity, what is the acceleration. Maybe we can do this way. We may try to get the graph of the function, but I'm not sure if without any calculator and any equipment, if we can get the graph. It's not extremely difficult because we can see it's the odd function. T is taken to the power of 1, t is taken to the power of 3. That means odd will be, the function will be symmetric with respect to I don't want to draw it, but if this is the position function, this is time, definitely 0, t equals to 0 is one of the x-intercept. And then I'm assuming the graph will be like this. Okay, but we don't know these maximum points. We can guess that is around 5, then we will have this situation. And when we have this situation, we know that velocity, because the slope of the tangent is positive, and the tangent lines are getting steeper. Yeah, the tangent lines are getting steeper. That means Oh, actually, no, not steeper. Oh, no. That's the tangent line. This is actually less steeper. Okay, I mean, velocity is positive because velocity is positive slope, but the rate of change of the velocity, which is acceleration, the lines are getting less steeper. They are almost approaching horizontal line. Then the rate of change of the velocity is decreasing, the acceleration is negative. And when they have opposite signs, sign is the object in this situation, the track is slowing down. Okay, but of course we don't exactly know how to draw it, but we can use calculus part. We can one more time look at the velocity. Velocity is 25 minus 0.9 t squared. Okay? We may look at this graph. This graph is not bad to analyze because it's parabola t squared. Parabola with the leading coefficient negative and y-intercept 25. That means it's 25. We're not interested in that part. Okay? And yeah, we will have some x-intercept, but we're not interested here. And then that's the velocity actually. Okay? So we can definitely see the velocity is placed. We have to figure out where is 5 because we're looking at the interval between 0 and 5. I would say 5 is somewhere here because that x-intercept where the velocity is 0, we can even try to predict velocity is 0 if 25 minus 0.9 t squared equals to 0. Then t squared is 25 over 0.9. And that means this will be square root of 25.9. Now we can maybe figure out square root of 25, but we have to be careful with the, let me write 25.9 is 9 over 10. I can put 10. Oh, okay, I can put 10 on the top. I'm just trying to figure out that this will be 5 over 3 times square root of 10. I mean, this number is definitely less. I mean more than 5, right? Because 5 over 3 and square root of 10 is more than 3 because square root of 9 is 3. I mean, this is a little bit more than 3. And then even if we would, that means we will still, if this will be exactly 3, I can cancel out and I can say it's 5, but it's more than 3, then I will multiply 5 by a certain like fraction. This indicates that that number is more than 5. Okay, that means this is this. We don't have to know. I'm just trying to, okay, that's me now. And even if we don't, we can still analyze. That's mean now let's see, this is velocity. Velocity is placed above the x-axis between 0 and 5, then is positive. And looking at the rate of change of the velocity, I can indicate blue. I can draw a tangent, but now we have to be careful, it's different graph. Now we only looking at if these tangent lines, are getting steeper, right? Or maybe if no, let's be exact in the values. What about the values? I mean, this is quite, yeah, we can see it's getting steeper actually, but in the negative direction. If this slope is negative half, this is steeper, -1, or in the negative direction, -2. Right? I mean, if the numbers are increasing in the negative direction, and that's the numbers because the slopes of the velocity is the rate of change of the velocity, is the acceleration, the numbers are getting smaller. Okay? That's what we just prove using different tools that we do have different signs. Velocity and acceleration differ in size, in sign, and the object, the track is slowing down. Okay, that's what we need to know. I can say the track is slowing down on that interval. Okay, perfect. Exercise number 2, similar. Find the acceleration at the time t equals 5 minutes of a helicopter with the position function being equal to s of t equals to 300t minus 4t cube meters. Plot the acceleration, the second derivative, on the interval from 0 to 6, okay. And the question is the helicopter speeding up or slowing down during this time interval? Explain. Okay, let's start. We have position function 300t minus 4t cube. Again, the third degree polynomial. Let's don't draw the graph. Let's figure out the velocity first, because we have to reach acceleration, the second derivative. Velocity is the first derivative, 300 minus 12t squared, and acceleration is negative 24t, negative 24t. Okay, velocity and acceleration is not bad to draw it, since we can draw nicely quadratic function. Okay. Okay, and actually acceleration at 5. We can substitute 5 because we have to find negative 24 times 5. This will be 120, negative 120 meters, okay, per minute squared, because it's distance over the time and over the time again. Okay, it's negative. Acceleration is negative at 5. Okay. How we can answer if it's speeding up or slowing down? We have to figure out what is the sign of velocity and acceleration. And that's one of the easiest way. And we understand the whole concept, of course. The steepness of the tangent line. And so what I can do, I can draw on one plane. This will be time. I will not indicate the y-axis because I will put the velocity and acceleration. Acceleration is easier because it's just the linear function, negative 24t. Linear function with the slope negative 24. Oh, quite steep, but we're not interested here. Let's just say this. This is the acceleration, okay? We're not interested in the negative time, of course. Okay, velocity, it's parabola. And we can see 300 minus 12t squared. Again, it's parabola, which is open down. 300 is 300, oh, my scale, it's the y-intercept, and it's open down. Oh, a little bit too, because the leading coefficient. Okay. Actually, we're not interested. Oh, no, I can do this. I can write, we're just not interested in this side. Yeah, we're not interested. We just looking this. We don't know again. We still know. We don't know the x-intercept. Yeah, the 0, the time. What is the time when the velocity is 0? We can figure out this one. This will help us. Velocity is 0 if 300, my pen is not 12 equals to 0. This will be 300 divided by 12. We can divide by 3 and we can divide by 4. Okay, 25, then t is actually 5. We're not interested with negative. Okay, that's good. But we have the situation that we're looking at the interval between 0 and 6. And that's good to know, because we remember the previous question, we were like we didn't yet, the velocity didn't change the sign. Okay, I mean, what we can do, this is important, and this one. I can draw a line that's actually this graph, how can I say? This is velocity and this is acceleration, okay, on one graph. And we have to just figure out where the velocity is positive, where is negative, and where the acceleration. Acceleration actually is negative for all of the values between 0 and 6, because it's below the x-axis. Velocity is positive above the x-axis between 0 and 5, and negative here. I mean, when we will divide this, because we're looking at from 0, 5, and 6. I mean, on that time interval between 0 and 5, we may notice that velocity is positive, right? Velocity is positive and acceleration is negative, above, below. Then this is the case for slowing down. You can see how nice we can do. Slowing down. Yes, the helicopter is slowing down. Okay, now that interval between 5 minutes and 6 minutes of the trip, we may see that velocity is below, it's negative, and acceleration is negative. Both of them, they have the same sign. This is the case for speeding up. Speeding up. Okay, that's we have two different situations. Between 0 and 5 minutes is slowing down, and then between 5 and 6, speeding up. Okay? Always the sign. We have to figure out the sign of the velocity and acceleration. Okay. Also, let's look at a couple of problems which are related to the Galileo equations. Okay. Galileo discovered that the height s of t and the velocity v of t at the time t seconds of an object tossed vertically in the air near the Earth's surface are accurately represented by these formulas. And you probably saw this formula. Position function is defined as an initial position plus initial velocity times t minus 1/2 g. G is the acceleration due to the gravity, t squared. And when we compute the derivative of this, we will get the velocity. Derivative will give us, because we can consider that this is constant, and this is constant. T is a variable. Then derivative of s sub 0 is 0. Derivative of that part is v sub 0, and derivative of this part is 1/2 g times 2t. 1/2 times 2 is 1 gt. Okay, so we have v sub 0 minus gt. Of course, g is the acceleration due to the gravity. If we using the metrics, we will say 9.8 meters per square seconds, or if we using the imperial system feet, then we can say 32 feet per square second. Okay, that's the numbers. We also familiar with these numbers. Okay, so just in case if we have this vertical situation, that's the formulas for the position function and the velocity. S sub 0, of course, is the initial position. One more time, v sub 0 is the initial velocity. Okay, now let's look at the question. Before the question, I also have this observation. Probably it's quite obvious. Maximum height of the object. Like, how can we find the maximum height? We definitely can observe that if if the rate of change, yes, if the rate of change is like positive, function is like increasing, and then is attaining this horizontal situation. For the horizontal tangent, slope is 0. If the slope is 0, derivative is 0. If the derivative is 0, velocity is 0. So this will be the moment that the object is obtaining, is like attains a maximum height. Yeah? If the velocity is 0, the rate of change is 0. Yeah? And then is falling down. It's like rising, attaining this situation, yeah? Slope of the tangent 0, and then falling. And that's the condition for the maximum height. That's how we can find, solving this, we will find the time where we have maximum height. When we have the time, we can use this t, substitute to the s, to the position function, and get this. This will be s of t, get this maximum height. Okay, we good. Let's look at this question. A projectile is launched upwards from ground level with an initial velocity of 60 feet per second. Question A and B. Is a projectile rising or falling at the time 1 second and then 3 seconds? When does the projectile reach maximum height? And what is the maximum height? Okay. So what we will do, we will start with, of course, Galileo's equation. And the position function is defined as an initial position, initial velocity times t minus 1/2 g t squared. Okay. And of course, initial, initial position is 0 because we're starting from the ground. Initial is 0 and initial velocity is provided 60 feet per second. Okay, of course, g, the acceleration due to the gravity, since we're using feet, we will say that this is 32 feet per second squared acceleration. Okay, that's what we did, figure out these numbers. Now let's see what is the equation. This is 0, this is 60t minus 1/2 32 t squared. Then our position function is defined as a 60t minus 16t squared. You can see we did create the equation. Wow. And now, okay, that we do have an equation. Part A is asking if the object is rising or falling at t, 1 second and 3 seconds. We know that if the velocity is positive, object is rising. If the velocity is negative, object is falling. Okay, let's find the velocity. I will differentiate s of t. 60 minus 32t. That's the velocity. Let's find out the value at 1. 60 minus 32 times 1. 28, of course, feet per second. And let's substitute 3. 60 minus 32 times 3. It will be 96 minus 60 negative 36 feet per second. This one is positive, this one is negative. Right? So we can say that is when it's positive, the object is rising. So we can maybe say rising and falling here, okay? Because it's negative. Negative slope is negative, function is decreasing. And that's what we can figure out the answer. That means it's definitely the projectile is on the way down and the velocity is negative. rising is on the way up. Okay, we did this. Now, what about part B? When does the projectile reach maximum height? We know the condition, and I know that you're probably telling to yourself that this is the condition when the velocity is 0. At that moment, the object is reaching the maximum height. Okay, where is the velocity? Velocity was 60 minus 32t. 32t equals to 0. Then t is 60 divided by 32. Not a nice number. We can divide by, what we can divide by 2, 30 over 16, and we can still divide by 2. I know because we do not have calculators. 15 over 8, almost 2. Yes, because because if this will be 16 over 8, it will be 2. Okay, that means it's 2 seconds. I mean 15 over 8. We can keep this. Okay, that means at this moment, velocity is 0. At this time, 15 over 8 seconds, the velocity is 0. That means this is, if they asking when does the projectile reach the maximum height, at that moment, almost at 2 seconds, if I will approximate this. But now, what is the maximum height? Height maximum will be the value of the position function at that time, 15 over 8. We have to substitute. Let's substitute 60 times t. T is 15 over 8. Now I'm using the s of t, the position function, minus 16, and then t squared, 15 over 8 squared. We need a little bit of time, but I did my calculation, and the answer is 56.25 feet, 56 1/4. You can try, maybe we need a calculator, maybe not, maybe we can still figure out without the I think we can figure out without the calculator, like trying to factoring out. Do not take these numbers to the power of 2. Cancel out some numbers and we can definitely figure out, but okay, either way, we have the answer. That means this is the maximum height. I will not draw the graph because actually the position function is quite nice. It's the parabola. Yeah, parabola, open down, of course, because the object is rising and falling. And I don't know if I want to 0 and another value, but this is definitely 15.8. And the height, maximum height, is 56 1/4. I can use this. That's the position function. That's the time. I will not figure, one of the 0 is 0. I will not figure out the other x-intercept. Okay. Another question. A ball is tossed in the air vertically from ground level, returns to Earth 4 seconds later. Find the initial velocity and maximum height of the ball. Can you do it? You may pause the video and try to solve it. We definitely have to use the Galileo's equation. You can start, you can even think what was done in exercise 3, and I will be so happy if you will solve it without me, but okay. I hope you paused the video and now you are back. Let's start with Galileo's equation because it's tossed into the air vertically. That's how I know to use them. Position function is initial position, initial velocity times t, minus 1/2 acceleration to the gravity and t squared. Since we started from the ground position, initial position is 0. We don't know initial velocity. This means I can change this equation only to this form. And okay, one more thing, I can say G, acceleration to the gravity, since we don't know, Maxim, we don't know what is, if we using meters or if we using feet. Let's say meters. I don't find the maximum. We're supposed to have this. Okay, I will use the metrics, and let's say 9.8 meters per second squared. We also have to know this 9.8 and 32. Okay, 9.8 t squared. The final equation for the position function is, let me, okay, that means the equation is v sub 0 initial velocity times t minus half of 9.8 is 4.9 t squared. Okay. But we have to find the initial velocity. How we can find out? We have some information. We know that after 4 seconds, the ball returned to Earth. Then after 4 seconds, the position function was 0. Okay? That's what we built the model. And now let's see. I will take the equation and substitute instead of t time 4. How can I organize this? Let's say this, v sub 0 times 4 minus 4.9 times 4 squared equals to 0. Okay, I will just move this s at 4. Okay, then we have 4 v sub 0 and then 4.9 times 16. And let's solve this for v sub 0. When we solve this for v sub 0, we will have 4.9 times 16 over 4. We can simplify. 4.9 times 4, it's almost 20 because it's 5 times 4, but we have to subtract 0.4, right? 19.6 meters per second. Yes, we did get initial velocity. Excellent, excellent. Now our equation we can get back and we can say the position function is 19.6 minus 4.9 t squared. Oh, t, I missed t. Yeah, because because we did compute initial velocity using the given information. And the maximum height, we know that the maximum height is happening when the velocity is 0. First of all, velocity. Velocity is derivative 19.6 minus 4.9 again times 2, 9.8t, and velocity equals to 0 if 19.6 minus 9.8t equals to 0. T equals to 19.6 divided by 9.8, and I believe it's exactly 2. Okay, exactly 2 seconds. Okay, and since we see the quadratic function, it's parabola, open down, and since that was 4, we can even, like without, that's position function, that's time, even without solving this equation, we can figure out that 2 seconds because it's exactly parabola is symmetric, exactly in the middle. Okay, that means at 2 seconds, we have maximum height happening. But what is this maximum height? We have to take, let me put the height, maximum. We will take that time and substitute to the formula of the function s. And it's actually interesting, when we substitute 2, we will get 19.6, the same like the initial velocity, but it's just coincident, okay? It's not always this scenario. I mean, this maximum height, it will be 19.6 meters. The same like initial velocity, like slope, slope of this line here. Okay, that's interesting. Okay, yes, we practice Galileo's equations, and I have one more question and we will be done. Just answer which statement is true. Okay? Just kind of like finalize the speeding up, slowing down, but with respect to the velocity, decreasing, increasing, negative, positive. Consider the graph of the distance s from the origin as a function of time for a car trip. So we can see nice the shape. Time in hours, distance in kilometers. And we have three questions, 1, 2, and 3. And we have to figure out which option is correct, A, B, C, for each of them. Identify the correct statements. Okay, over the interval between half and 1. Between half, where we are, between half and 1. That means this is the first one. Can maybe use different colors for different statements. Okay, on that interval, we have to figure out if the velocity is decreasing, velocity increasing, velocity negative. Definitely looking at the slopes of the tangent, which is the velocity, it's not negative, because when we draw the slope positive, 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 I mean, this is not a good statement. And now I kind of draw it too thin, but it was quite steep, and then less steeper, less steeper. The values of the slope are decreasing. Slope is the rate of change, velocity is the rate of change. Velocity is decreasing. Okay, now second, over the interval from 1.5 to 2. Oh, it's a little bit crazy because we're changing, which somewhere in the middle, the situation change. But when we draw the tangent lines, tangent, 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 not even thinking how they behave with respect to the increasing, decreasing, they are definitely negative. Velocity, because slope of the tangent is the rate of change, velocity is the rate of change, is negative. It will be a little bit confusing when we have to answer if the velocity is increasing, decreasing, because we may notice halfway we have this situation. From almost horizontal, the slopes are getting steeper. And then at this point, they again, that means steeper in the negative direction, but definitely are getting smaller, I can say. But now it's in the middle, and then again are getting less steep. Right? As we can see, we can't really analyze this. We will have inconclusive answer on the entire interval. If I will split this interval, then we can say something. Yeah, but they asking for the entire interval. That's the reason that we cannot answer, because it's less steep, steeper in the negative direction, of course, decreasing, we have to, and then again is less steep in the negative direction, is increasing. Okay, that's, we will not answer this question. Okay, and the last interval from 2 to 2.5, this is just one. Oh, we're not changing? Okay, we're not changing, we have just this situation. Okay, that means this situation, we know it's for speeding up, if we want to say this way, because the slopes are positive. That means velocity is positive. Oh no, that's wrong. And it's getting steeper and steeper. Velocity is increasing. Oh, it's the same situation? No, not the same situation like one. No. Now we can see the slopes are getting steeper in the positive direction, bigger, increasing. Okay, enjoy the speed and velocity connections. Thank you.